There we go. Okay, so section 21.4 deals with what's called transmutation. And we're going to talk a little bit about nuclear energy and where nuclear power plants get their power from. So, transmutation or nuclear transmutation is just the conversion of one nuclide into a different nuclide. So, you're basically changing one nucleus and changing it into a different type of nucleus. And that can occur a number of ways. It can either occur by radioactive decay, maybe a beta decay or an alpha decay, right? Or it can also occur by the reaction of a nucleus with another particle. And so the first person to do nuclear transmutation by the reaction of a nucleus with another particle was Ernest Rutherford, the same Ernest Rutherford that did the famous gold foil experiment. And he just took a nitrogen 14 nucleus and he hit it really hard with an alpha particle to make a brand new nuclide. He made oxygen 17 and he also yielded a proton in that reaction. And the way that you nowadays that we do transmutation reactions is that we use what are called particle accelerators to get the particles like an alpha particle or different types of particles moving really quickly. Okay, and they use superconducting magnets and vacuums to avoid having any gases or any resistance to the movement of the particles, and they basically get the particles to collide, right? And if you've studied the CERN, there's a little write up in our textbook about that, and you could read more about particle accelerators. But anyhow, what's the whole point of this concept of nuclear transmutation, of converting one nuclide into another? Well, if you look at the upper echelons, or what I call the dusty area of the periodic table, the once you get up into the actinide series past uranium, you have all these high molar mass elements that over in my periodic table that I'm looking at right now, a lot of them have masses that are in brackets, right? They're in little brackets. And so we sometimes call those the synthetic elements. I've heard them called that, or the artificial elements, okay, because they're synthesized, right? That's where the name synthetic elements comes from, because we're basically taking a nucleus and we're combining it with another particle. Okay, and so these are made by nuclear transmutation. So the elements beyond uranium are called the trans-uranium elements, or again, sometimes artificial or synthetic elements. And you see a bunch of them here, like americium, curium, californium, einsteinium, mendelevium, nobelium, Rutherfordium, Glenseaborgium, and the last one. So anyhow, how do you make these synthetic elements here, right? They have these really high atomic numbers. Well, we're not going to get into all the nuts and bolts, but you can see that what they're doing is they're taking some other kind of nucleus, another radioactive nucleus in most cases, and then they're smacking it with another particle, like maybe a neutron or an alpha particle, right? Or maybe they're using a bunch of neutrons, right? And they're smacking it, or maybe with a stable nucleus like carbon 12. But nevertheless, they're using transmutation to form these trans-uranium elements, these heavy elements, these synthetic elements. And so this is an example of how we would use nuclear transmutation. Well, if we have a really heavy nucleus, we mentioned way back in the last lecture that when we looked at the concept of nuclear binding energy per nucleon, we said that when we have a nucleus that's heavier than iron 56, those elements are going to tend to undergo what's called fission or splitting. And fission is nothing more than when a heavy nuclear particle breaks into smaller nuclei, okay, to make something that's going to be more stable. Now, when we take a stable nucleus like uranium-235 and we bombard it with a neutron, what we end up making is uranium-236, which is unstable. And that uranium-236 is what is going to undergo fission, right? This is the fission process right here. Now, fission of uranium-236 can yield a whole holy host of different nuclides. But anyhow, in this reaction that I have here in the red box, it shows krypton-92 and barium-141 being produced, as well as 3 neutrons and some energy. And this is where the energy in nuclear energy comes from, because we get a lot of energy from a nucleus. If you just evaluate the amount of energy that you get from the fission of one uranium nucleus, it doesn't look like a whole lot. But hold on, if we have 1 mole of uranium, it's only going to weigh about 230, 240 grams. It's not a whole lot. So even with a small amount of uranium, we can generate a huge amount of energy. And this process is self-perpetuating. And that's the last thing I think we're going to talk about today is the whole concept of a chain reaction. And so we'll talk about that in a little bit. But the whole idea behind nuclear power is that the energy that's produced can be used to heat water, which can generate steam, and the steam can be used to run a turbine, and the turbine can be used to produce electricity. So here is a figure that I got from another textbook that I thought was really good. We have the uranium-235 being smacked by a neutron. You end up with uranium-236, which it looks like it's got a really funny shape here. It's showing that it's not very stable, right? Now, 2 slides ago, or sorry, this slide, I said it was yielding krypton-92 and barium-141, but I told you those aren't necessarily going to be the products. There's a whole range of products that we can get, which I'll discuss in a second. So here in this particular reaction, it's saying, okay, well, the products are strontium-90 and xenon-143, but look, we're also producing 3 more neutrons. Well, a neutron was all you needed to get the reaction started, didn't it? Okay, so I know where that's taking your mind probably is like, hey, chain reaction, right? I'm making even more neutrons. We're going to talk about that in a second. But before we do, I want to think about how much energy is going to be produced. I'm not going to go over the whole a whole calculation in its entirety, but the amount of energy that's produced from E is equal to mc squared. We know what C is. What's our M? The M is the mass defect between the sum of the mass of the uranium-235 and the neutron, right, that we're starting out with, minus the mass of the products and the 3 neutrons, right? Those are all products. So our starting materials, right, subtract the mass of our products, right? This is an intermediate here, okay? So when you do the math, look at this. You end up with the energy that's being released as being 3.3 times 10 to the negative 11 joules for every uranium-235 atom that we have. And again, it doesn't sound like a whole lot, does it? But remember that there's 6.022 times 10 to the 23 uranium-235 atoms in 1 mole. So what if we had a mole of those? We take this number, we multiply it by Avogadro's number, and what do we get? 2.0 times 10 to the power of 13 joules per mole. Okay, that is a lot of energy, my friend. You look at the amount of energy that's yielded from the combustion of 1 ton of coal, it's 5 times 10 to the power of 7 joules. So that means we have about 2.5 million times more energy produced from the 1 kilogram of uranium-235 or from a mole of uranium-235 than we would from a whole ton of coal. So kind of fascinating there. We end up producing large amounts of energy from nuclear fission. Well, as I told you, if you take uranium-235, okay, and you smack it with a high-speed neutron, I told you that you're going to end up with the unstable intermediate, uranium-236. But here's what I was saying, you guys. I said the products aren't always the same, okay? It depends. There's a whole range of products that can be formed, which aren't even limited to the 5 reactions that I have here. But you see that you either end up with something with a mass of around 90, 87, what do we got, 96, 97, 92, right? We end up with something in this range right here between 85 and 105. And then we also end up with a nuclide that has a mass of, let's say, 144, 146, 137, 137, right? 141. So somewhere in this range right here, which is 130 to around 150. So again, the conclusion is that the nuclear fission of uranium-235 produces a whole pile of different fission products, but typically you have one isotope with a mass number around 85 to 105, and you get another isotope that's around 50% heavier. Okay, so somewhere around the 130 to 150 range. And again, we can abstract a ton of energy from that. Well, again, you see that besides producing the isotopes, you also end up producing neutrons. Sometimes it's 3, sometimes it's 2, depending on the nuclides that are produced. But again, what did we need to kick the reaction off, right? All we needed was a neutron, okay? And you can imagine there's a serious consequence with this, right? What if we have, oh man, came out really fuzzy, fiddlesticks. Anyhow, I'll try to fix this in the slides. I'm sorry that this came out fuzzy, but let's see if you can just follow along with me here. So what's, dang it, what's being shown here is that this is one neutron. So this is a neutron here. And this is uranium-235. So this is uranium-235, okay? You smack it, you make uranium-236. They're not showing that here, but you get a couple of products, right? Here they're showing that you end up with krypton-93 and barium-140. I know you can't tell by the slide, but the whole point is this, is that you end up producing 3 neutrons, right? You end up with, here you have a total of 3 neutrons, okay? And those can react with 3 more atoms of uranium-235, and they're going to react to produce a total of 1, 2, 3, 4, 5, 6, 7, 8, right? This one only produced 2 neutrons, but they produce a whole bunch more neutrons, and that is a nuclear chain reaction, okay? So if you have enough uranium atoms, you can get a chain reaction occurring. So any material that can undergo a nuclear fission chain reaction, we say that that material is fissile or fissionable. Now, fissionable is a little bit different than fissile. I usually just say that it's fissile, that it's able to undergo fission. But with respect to material that is fissile, there's 3 types of masses or amounts of fissile material that we have to take into consideration. A critical mass, a subcritical mass, and a supercritical mass. So see if you can follow along with me here. It says, if the amount of fissionable material, and I'm reading from right here, I'm just reading straight off the slide. If you have enough material to support the chain reaction, we call that the critical mass, okay? Now, you might be thinking, and this is what I thought the first time I heard this when I was a university student. I thought, well, jeepers, what does that even matter? I mean, I thought that if you have uranium and you hit it with neutrons, you're going to make energy, right? But hold on. You have to have a certain amount. Now, why would that be? Because if you have an amount that's too small, it doesn't sustain the chain reaction. That's called a subcritical mass. Now, why would if you don't have enough, why wouldn't it sustain the reaction? If you're like, okay, well, maybe it just means that I'm going to get a smaller amount of energy. No, it means that it won't sustain the chain reaction. The reason why is this, okay? When you have a subcritical mass, look what's happening to most of the neutrons, okay? Most of the neutrons are actually escaping the surface, right? Because think about it, the smaller amount that you have, the greater surface area you have per particle. So it says here that in a subcritical mass, the fissile material, you've just got too small a volume, and it allows too many neutrons to escape or leave the whole mass that you've got, right? This is the mass of all your uranium-235. But if all the neutrons are escaping it, then they're not colliding with any uranium-235 atoms, and then you don't have a chain reaction, right? Because most of them are just escaping. Once you get to a critical mass, okay, once you get to a critical mass, then you have enough material that the ratio of neutrons that are escaping, some of them can escape, but it's going to be much smaller compared to the entire volume where you're going to have a lot more collisions occurring. So you're going to have less neutrons escaping that material. And this means that you've got enough material to allow the chain reaction to occur. Now, a supercritical mass, that's when you've got so much that the rate of the chain reaction keeps increasing and increasing and increasing, okay? So those are the differences between the two, or between the 3, the critical mass, subcritical mass, and supercritical mass. But I want to focus on the 2 that I have highlighted here for just a second, the critical mass and the subcritical mass. In terms of the atomic bomb, so you guys have all heard of the nuclear bomb. So the first bomb here, this is the type of bomb that was dropped on Hiroshima back in 1945, so August 6th. So this is pretty much the end of the Second World War, and there's some really interesting history behind that, and the Manhattan Project, of course, if if any of you guys know anything about that. But how did that atomic bomb work? Okay, all it had, if you think about it, once you understand a little bit about what a critical mass is and a subcritical mass, it's actually very ingenious. What they did in the uranium bomb, okay, is that they had 2 masses of uranium, okay? They have a mass here and another mass here. Both of those masses are subcritical masses of uranium-235. So Even if you do bombard it with a neutron, it's not enough to sustain a chain reaction and release a whole pile of energy. So what they did is they separate them. Okay, so here's the distance between them, and all they did was just have some TNT. Very simple, right? All you have is a detonator and some conventional explosion. I don't know if it's TNT or not. That's neither here nor there. But let's just say it's TNT. What happens when the detonator goes off? It fires off the TNT and it makes this clump of uranium-235. It goes kapow! And it smacks into the other massive uranium-235. And now you have a critical mass. Okay? Now you've got a critical mass of uranium-235. Now you've got a pile of collisions and you're going to release a ton of energy. And that's the whole concept behind the uranium bomb. Okay, or the nuclear fission bomb, whatever you want to call it. Now, and I don't remember the names of the bombs. I'm sure that somebody in the class could tell me the names of those bombs. That's neither here nor there. It's got nothing to do with the class. But the plutonium bomb, I'm not really an expert on the plutonium bomb. I haven't read as much about it. But the plutonium bomb basically runs on the same kind of concept, the same type of concept, is that you basically have a hollow core in here with some plutonium. And then what you do is when it was detonated, okay, the conventional explosive basically took all that plutonium in the center and crams it all together. It compresses it, okay? That leads to a concentration of plutonium that's bigger than the critical mass, and there you go. Then you've got a big, big explosion, and you release a ton of energy. So all they were doing with the atomic bomb is basically harnessing, where is it? This concept here, right? The same type of concept, E equals mc squared, right? The whole concept of the chain reaction and the concept of a subcritical mass in the terms with respect to the uranium bomb, and a critical mass and a supercritical mass, of course, in the plutonium bomb. And that's the whole idea right there. That's the whole concept. And yeah, that's it. Pretty cool.